Each year, MIT Technology Review selects 35 visionary leaders shaping the future of technology, research, and entrepreneurship. Today, we're joined by MIT Technology Review's Amy Nordrum and two trailblazers from this year's list. They'll dive into their groundbreaking inventions, the mega-scale Immune Dictionary and the world's first flexible neural recording device. They'll also discuss what's next on the horizon for technology. Stay tuned. Well, thank you so much, everyone here, for coming to this event. We are first going to introduce ourselves, so I will go first. My name is Ree. I am the moderator.
Hi, everybody. I'm Amy Nordrum, Executive Editor of MIT Technology Review. Hopefully you know who we are, but if not, we're a newsroom of journalists based here on MIT's campus. We're editorially independent from the Institute, so we don't cover MIT. We write about the broader world of emerging technology, covering AI and climate tech and biotech. And my role, part of my role in the newsroom is to oversee our annual list that we put out. We have a list of 10 breakthrough technologies, a list of 15 climate tech companies to watch, and the list we're talking about today, which is 35 innovators under 35.
Thank you so much for inviting me here, and it's a great pleasure to meet all of you. I'm Ang. I'm an assistant professor at Harvard University, and I lead a research group that uses systems biology approach to understand the immune system. So we use a lot of big data to understand the complexity of our immune system and develop more effective immunotherapies.
Hello, everyone. Thank you for being here. I'm Claudia Cea, and I'm currently a postdoc here in MIT in Polina Anikeva's group. I'm starting as an assistant professor next July in electrical engineering department at Yale, and I work on highly flexible and conformable neural interfaces.
Amy, I want to ask you some questions about MIT Technology Review, as well as 35 innovators under 35. So I know some very famous people have actually made it to that list, including Mark Zuckerberg. So tell us more.
Yes, so this is a list that our newsroom has been producing now for 25 years. The first one we put together, I was not there, but the team put together to commemorate our 100th anniversary as a publication. And this year we're celebrating our 125th anniversary as a publication. So we've been putting this list together for quite some time. It actually started out as 100 innovators in the very first couple of years. Now it's down to 35. Thankfully, because it's still quite a project to put it together. But as Ree says, we've had some pretty big names honored on the list over the years, including Zuckerberg, including Helen Grenier, the founder of iRobot, was on the very, very first list in 1999. Lisa Su, who has a building just down the street named for her and is the CEO of AMD, was on the list in 2002 when she was 32 years old. Andrew Ng, who many of you know, AI pioneer and serial entrepreneur, he was on the list when he was an assistant professor at Stanford in 2008. He actually also has been a judge for us in previous years and wrote the introductory essay to the package last year. And I really love this project because the way that we think about it internally is it's a list that explores, and identifies some of the most fascinating people working across all these different areas of research. And by understanding what they're working on and what they're focusing their talents and energies on, you can sort of see what's coming up in technology in the years ahead, because these are some of the leaders in their fields.
And tell us a little bit about the selection process. I know that these people are not just sourced from the U.S., but globally, right? So how do you go about that?
Yes, and I'll just give a plug. If you would like to be on the list of innovators under 35, we have an open call for nominations because we want to make it accessible to anybody who wishes to put themselves forth. And so you can nominate yourself or you can nominate somebody that you know. And nominations usually open in November, so keep an eye out for that in the coming month, and they will close in January. So we take nominations. People send us their own portfolios or suggestions for people that they know. We also obviously have a team of reporters that are monitoring different beats every single day, and so we asked them for recommendations. Who have you spoken with in the last year that you think might be a good candidate for this list? Who are you most excited about or interested in seeing as a candidate? We get hundreds and hundreds of nominations, which is a testament to these two for making the final list. More than 500 nominations every single year. So it's a big process once we close those nominations in January to sort through those nominees and figure out who's kind of on our short list. And to do that, we enlist a couple of, or a couple dozen really, of judges. So these are experts in these different areas, whether it's material science or biotech or climate technology. And we ask them to review the candidates in their category and score them. And we try to get a couple of judges for each semifinalist, I'll call them. And these judges are really weighing in on, what is the nature of the advance that this person has made in this field? Was it incremental or was it truly, a game-changing innovation? So the judges are reviewing all of these semifinalists and scoring them, and we're getting their input. Some of them are actually past innovators themselves, so they've been through the process. And so that gets us down to a shorter list, and then our team of editors looks across that list and makes the final calls. And there's also licensing partners we have in different regions that do regional lists as well. So there's Innovators Latin America, there's Innovators China, there's other regional lists out there too.
For 2024, the innovators that were really driving better health, more stable climate, and greater equality were chosen. So what was the kind of thinking behind these themes?
Yeah, one thing I always like to say about our newsroom is that we don't write about technology for technology's sake. We are always concerned with the impact of technologies, and we want to put them into context of how they will go forth and change our world and the way that we live and work. And so we're always thinking about economic and political and social implications and impacts. And so we try to focus our coverage on some of the most impactful areas of science and technology research and write about them kind of through that lens. We have Tim Latimer from Fervo, enhanced geothermal company, for example. And then we have material science and biotech, and many of the innovators in those spaces are either working to improve people's lives and by improving their health, so a very real concrete impact on people's well-being, or they're innovating really cool new materials or solutions to other problems. We have Andy Wallace of Robigo on the list. She is working with microbes to try and design them in a way that they could reduce the amount of pesticides that farmers need to put on their fields, which is a huge generator of greenhouse gas emissions. So there's a lot of examples like this across the whole list in different spaces where people are tackling these big problems that we face as a society, or just also working to improve people's individual health and well-being.
Ang and Claudia, right? So you were both heavy into engineering, right? Computer engineering as well as electrical engineering. So how did you get into biology?
So in my lab, we're still half computational, half experimental. And to answer a question about the last 15 years of journey of combining these two fields, so I got my PhD from the Harvard MIT Health Sciences and Technology program. I majored in medical engineering. And in the last 15 years, I did immunology research at the Broad Institute. And before that, it was at Yale University. And before that, it was at the University of Toronto. So I started my career studying electrical and computer engineering with a machine learning focus from the University of Toronto. That's where I got my undergrad. And as you probably know from this year's Nobel Prize in Physics, which was awarded to Professor Geoffrey Hinton at the University of Toronto, who is considered the godfather for modern deep learning. So back then, that was first year college for me was 2008, 2009. It was already very hot. Everybody was talking about it all the time. And I naturally joined a machine learning lab. And I started to develop machine learning algorithms to study childhood arthritis, which is a group of autoimmune diseases, meaning the children's immune cells, for unclear reasons, start to attack their own tissues, their own joints. And that leads to a wide range of symptoms. And it was through this process I thought that the immune system is really fascinating. It's, the immune system is constantly working. There's so much in our environment, also so much in our body, like the body may develop cells that are abnormal, and our immune system needs to be able to constantly eliminate those cells and defend us from viruses, as we all know from the COVID pandemic. At the same time, the immune system is really involved in every major disease, like cancer, for instance. It's developed in part because the immune system is not able to effectively recognize and eliminate cancer cells. So I thought the immune system is just so fascinating, and I wanted to understand it better. But it was also clear that our knowledge of the immune system was very limited. So coming from a background in engineering and big data, which I knew was very powerful for understanding a complex system. And the immune system is a very complex system. So I thought it made a lot of sense to use big data to study the immune system.
So growing up, I used to watch with my little brother the popular TV show House MD, and we were both fascinated by the work that was portrayed in this show. Then my brother actually became a doctor, but I've always been very scared of needles. So I was like, okay, if I cannot face this fear, at least I can build devices that can be used in medical application. And that's how I decided to pursue my undergraduate degree in biomedical engineering in Italy. Then for my PhD, I switched to electrical engineering at Columbia University in New York. And even if I've been always very passionate about biomedical devices, I feel like this switch into electrical engineering was really essential, as I was able to learn and how to build all the circuits that are behind these biomedical devices. So I was able to merge this electrical engineering knowledge with biomedical engineering and material science. And this really helped me and led me to my discovery of the first fully flexible implantable neural device. And now I'm continuing this journey here now in MIT and hopefully in the future also at Yale.
I want to learn more about your breakthrough technology and the inventions. So tell us more, Anna and Claudia.
Yeah, I'm really excited to showcase our Immune Dictionary, which is the invention that got selected for TR35. So I'll give some background. Every field has a reference system. Like for chemistry, we have a periodic table of elements. And in genomics, we have the human genome reference sequencing. But in the field of immunology, such a reference system was missing. And as a result of that, people just learn one thing, one molecule, one pathway, one cell type, one gene at a time. It's very hard to really capture the full complexity of immune responses. But with some determination, we created the Immune Dictionary, which you can see from this artwork. It shows the 86 cytokines we studied in the Immune Dictionary. So cytokines are essential molecules to the immune system. You can think of them almost as important as the elements to chemistry. And the cytokines are so important. To date, there have been over 1 million studies that have studied individual cytokines or used cytokines in their research studies. And cytokines also are important therapeutic targets. So currently, cytokines represent over $80 billion of pharmaceutical drug market. The cytokine interferons are used to treat viral infections. So after we give patients interferons, their immune system get more activated, can defend us from viruses better. Cytokine IL-2, which is the first cytokine on the left upper corner, that is the first effective immunotherapy for treating cancer. It was used in the 1980s to treat a subset of patients who ran out of other options, and that was effective for a subset of those patients. So collectively, these cytokines represent major therapies, therapeutic target, biological information, but we never had the thorough understanding of how every type of immune cell in our body responds to each of these 86 cytokines. So we built an immune dictionary where we systematically measured how almost every major gene in our body, which is around like more than 20,000 genes, in every type of immune cell, we measured over 17 types of immune cells, responds to each of these 86 cytokines. And this gives us the first look into the effects of each cytokines in the body. So now people can develop more precise therapeutic strategies targeting each of the cytokines. For the last few decades, the use of big data to study the immune system was mostly done on a smaller scale, and it was mostly done as a supportive function for larger immunology discoveries. But now, we demonstrated that big data is now truly in the driver's seat for immunology discovery, and I'm very excited about this milestone.
I developed the first fully flexible neuroelectronic device capable of high-quality neural signal recording at the scale of a single neuron, as well as real detection of epileptic activity in real time. The main characteristic of this device, as we can see roughly from these images, is that each component is highly conformable and biocompatible. In addition, another interesting characteristic is that this device can be powered and relies on an ion-based wireless system that is called ionic communication. In this way, I was able to implant my device in the brain. I was able to transmit the recorded signal to an external computer by leveraging the presence of ions that everyone naturally has in our body. And I was using these ions also for powering the device wirelessly at distance through an intact tissue that is rich in ions. Of course, as we know, there's a lot of research groups, companies, startups that are working on this type of technologies on neural interfaces. Why mine is different from the others? In this case, the whole device, the overall device is fully flexible. And for achieving that, I focus on what is the backbone of these devices, which is a transistor. Each of us has millions of transistors in our phone, computer, but they're usually based on silicon, which is rigid in nature. So when I wanted to build like a fully flexible device, I was like, okay, so how can I do that? And the answer was to focus on what is the most essential component and make this most essential component fully flexible and conformable using polymers that can be nicely hosted in our body. And this is a very important milestone because, of course, there's, as I said earlier, a lot of devices for recording neural activity. But we want to build something that is ideally as soft as possible and as delicate as possible if we want to have it implanted. And this is coming from someone that is very scared of needles. So it's important that we fulfill this requirement if we want these devices to be hosted safely in our body and long term without the need of having to change the device because of failure after a few years.
We're going to have a couple of follow-up questions for the two of you about your respective advances. So Ang, we'll start with you. Tell us, you just told us all about this incredible immune dictionary you built. How have people been using it since you put it out there into the world?
Yeah, thanks for asking. People have been super excited. Like, it generates so much excitement around the world. The publication has been accessed more than 188,000 times, which is already one of the most widely accessed publications in biomedical sciences to date. And people in academia and industry have all come to us to contact us for various things. For example, in pharmaceutical companies, they have told us that they are developing cytokine-based therapeutics, and it was thought that specific cytokines act on specific pathways, but by looking at the Immune Dictionary, they learned those cytokines can also act on other cell types or other pathways. So now they're taking this additional information into consideration in their drug development process. So the goal is that our information can enable them to develop more precise, more effective, and safer therapeutic approaches for the next generation of cytokine-based therapeutics. In academia too, people have talked to us about how they have been developed cancer immunotherapy strategies. So people have been developing like a new combination therapies for patients that do not respond to standard of care. And the new strategies are effective for a small subset of patients. So we want to understand which patients are more likely to respond to these new therapies and which ones will not. And these therapies also target cytokines. So they look at the Immune Dictionary, they compare the Immune Dictionary profile with the patient profile, and they found that they were indeed able to predict which patients are more likely going to respond to the new therapies they're developing. So you can imagine this is a really game changer as now patients, when they're admitted to a hospital, if at baseline, before any therapeutic intervention, you can predict who is more likely to respond to which therapeutic intervention, that can make a huge impact on patient's life. In my own lab too, we're particularly interested in finding ways to boost the activities of immune cells. We identify strategies to enhance immune cell activities in ways that were never possible before.
Yeah, I mean, that must be so gratifying to put it out there in the world and get that kind of response. So, can you tell us a little bit more about the process of building this and why, in particular, big data was very well suited to this task of understanding how all these cytokines are working in the body?
So, as I mentioned, in the past, people have been studying cytokines for decades, and they were only measuring one thing at a time. And as you can imagine, what you can do by doing one thing at a time is quite limited. And also because different labs they have different experimental settings, and it's just very hard to gain a coherent picture of how the immune system works. And now, using big data, which involve massive scale experimental approaches, combined with very sophisticated computational approaches, we were able to measure the complexity of immune responses at least 2 orders of magnitude larger than the standard studies in the field. And that really reviewed the complexity of the immune system at a level that was never possible before.
And even with all this work that you've done, there's still a lot that we don't know about how the immune system works, as you spoke about in your earlier comments. What are some of the other fundamental questions in immunology that you're looking forward to hopefully someday having an answer to? What are you interested in further exploring or seeing other people tackle?
There are still so many diseases for which cure is not available. And we know the immune system is involved in cancer, autoimmunity, and now people know that immune system is even involved in like neurological disorders like Alzheimer's diseases or cardiovascular diseases. So as I look, the diseases for which a treatment is not available yet, which is like most of them, I'm interested in gaining a deeper understanding of the immune profiles in these diseases, as immunotherapies have been proven to be viable therapeutic strategies, and blocking or targeting specific cytokine pathways is very viable. It's been validated in many disease indications. I'm interested in understanding deeper into more diseases and how to really manipulate immune cells to create more effective immunotherapeutic strategies for like any disease.
Excellent. I have some follow-up questions for Claudia. So it sounds like your innovation was really about making new material that can function at necessary speeds, right?
So this ion-based transistor, they've been out there for the past 2 decades. However, they have one main limitation, which is their speed, meaning the time they need to switch on and off. And this was a main limitation for neural signal recording, because if you want to record something, we need a transistor that can switch on fast enough to record that signal. And in the case of activity from a single neuron, we are the order of magnitude of kilohertz, so milliseconds. And these transistors were not able to have this speed. So what I did with my work, I used new materials, and I changed the architecture of these transistors so that I could scale down the length. So what really defines the speed of a transistor is their length. So through novel materials and through a novel architecture, I was able to scale down this size from micrometers to nanometers. And that's what allowed me to get this speed that was fast enough to not only capture the signal from a single neuron, but also for processing it. Also, for being able to use this ionic communication system, this system only operates at megahertz speed. So that's why it was also very important to increase the performance and the speed of the devices. So I was able not only to capture this high spatial resolution signal